Sir, एक doubt.
Please. Okay, anyway, we can do like this. So this is called the horseshoe magnet. And if I call this is north, this is south. So the line joining the north and south pole is called the magnetic axis. In this case, how to join the magnetic axis? Should we draw something like this or directly here?
So you defined as a straight line, then I guess it should be direct.
Yeah. So the line joining the north and south pole is called the magnetic axis. Now the poles of magnet are the point at which the force of attraction force due to the between the iron fillings and the magnet is maximum. So you can just take a bar magnet or any magnet and you sprinkle the iron fillings around it. You can see the location at which the concentration of the iron filling is maximum is the pole actually. So we do have two types of length that we define here. One is called the geometrical length, which is the actual physical length, we call LGO. But the poles are not exactly at the edge, it is slightly inside. So the poles are found to be slightly inside, and the separation between the pole is called the magnetic length of bar magnet. So we can call this as L mag. And the ratio of L mag upon LGO is roughly 0.84. So it is 0.84 times the actual physical length or geometrical length. So what is pole actually? So it is the point at which the attractive power is maximum. What is pole strength? So pole strength we represent by M. It is analogous to the magnetic charge, or you can say it is analogous to the charge as in electrostatics. So you can call it a magnetic charge. So it is called magnetic charge, which is analogous to the electric charge in electrostatics. Now the convention for North Pole, we take plus in, for South Pole minus n. Okay, I hope this is clear. So this is something really fundamental. Okay. Now imagine a cylindrical bar magnet. And if you zoom out the surface part, then we can say that okay, it is made of tiny dipoles. Or dipoles means basically there are a small current carrying loop, right? And this current carrying loop you can draw by circle. We know that every atom will act as a dipole, right? Because the electrons are performing the orbital motion. If you draw something like this circle everywhere, okay, it's say everywhere. And if I assign the proper arrow sign, so try to understand this. If you have many circle, okay, let me do a separate collection of circle. 1, 2. Let me make it one as bigger. Now assign a current direction to each loop in the same sense. Do you realize something? All the internal current will cancel out each other, right? If you take any pair of circle, you can see they are opposite when they touch. So at the point of contact, what is it? The directional current is opposite, isn't it?
Yes, sir.
Think of any two pair of circle. Think of current in each circle. What do you think? The current will cancel out each other internally? Tell me, guys.
Yes, sir.
Do you all realize this? Hello, hello, hello.
Yes, sir.
So this is, can we say this is equivalent of a single current carrying loop like this? And it is similar to the electrostatics where, if you remember, where the dipole effect is only present at the edges. dipole, dipole. So all the internal charge will neutralize each other. What we are left with? Only this end and this end, which is the surface charge, right? And we used to call this as the uncompensated charge, if you remember, in dielectric. Hello, hello.
Yes, sir.
So similar to that, if you look from the top side, the circular loop will cancel out the internal current, and what is left is only the external current. And we can ignore the shape actually, because these are very small, and then therefore it is almost circular. So we can say that only the external current will remain, and that is why this current is nothing but a dipole, and this current is spread throughout the surface of the bar magnet. And this current, called the magnetizing current, is responsible for the property of magnetism to this bar magnet. So this is the atomic view of why bar magnet act as a magnet. Understood? So this bar magnet will have a surface current, and this surface current we can call as magnetizing current. Understood?
Yes, sir.
Yes, sir.
So every bar magnet is actually representing an infinite solenoid. Okay. So the property of bar magnet and property of solenoid is close to each other. So a solenoid you can think as a bar magnet, or a bar magnet you can think as a solenoid. And this magnetizing current is due to the non-cancellation of the atomic current. Okay. So that is how we, kind of establish the fact that a bar magnet is like a magnet, and the magnetism is arising even in bar magnet due to the some sort of current. And this current is giving it an equivalence to the solenoid. Okay.
Sir, is this measurable?
Yeah, if we can create it, we can make it measurable by some assumption. Okay.
Oh.
So let's say if I tell you that if I give you the linear current density, so let's say this is bar magnet is having the length L, and let I be the linear current density. So what is the total current? So linear current density means basically you can call this as J. I mean, if I is not convenient to you, the way we have assumed in the past also. So total current through surface is how much? It is J, right? If J
Yes.
is the current per unit length, then J is the total current.
Yeah.
So what is that? What is the total dipole moment? Total dipole moment of bar magnet. How much? So dipole moment is I into A.
Yes.
Can you say this is JLA? Because we are defining in terms of linear current density. So you can say IA, or you can say JLA is the dipole moment. Now, if you try to compare with the electrostatic, if I say the north pole is plus M, south pole is minus M as a magnetic charge, and if the separation between them, if you remember, is L magnetic, right?
Yes.
So technically, the dipole moment of a bar magnet should be ML magnetic, right? but roughly we take as physical length ml because of the it's a 0.84. So normally when we solve question, theoretically it is m into L magnetic, but practically we choose, I mean, we take the physical length as L, which is actual, it is more than the actual, right? Okay, so if they ask you the theoretical question, you have to say that a PM is ML magnetic and ML is the, I mean, of course, when we solve numerical, we take the ML part directly. I hope this is clear.
Yeah.
Okay. So kind of if you compare these two, because this is also dipole moment, so we can express dipole moment in two ways. ML, you can say JLA, and therefore, if you compare it, the pole strength, we can express as. Okay. So
Yes.
M equals to J, and J is a linear current density. So you can say a bigger cross section will increase the pole strength, isn't it? Because J is current per unit length, which is going to be same. Because as the length will grow, the number of loop will grow, right? We have one loop, then we have another loop like this, when we have next. So as L will grow, the loop will grow, but the J is kind of constant. So you need to understand, okay, this is constant. That's why we have, taken this into consideration to express the answer. So this is kind of constant, and then the bigger cross section area will have bigger pore strength. That is a kind of you can say equivalence. Okay, so we can always create these two equivalents. Okay, so you may need to express pole strength in terms of this, and see, this is a very interesting. You can actually express the pole strength of the solenoid. What is the pole strength of solenoid? Infinite solenoid. We can actually compare from here, right? So let's try to understand what is the pole strength of infinite. Pole strength of infinite solenoid. So what I know is the PM we know it is how much? Tell me.
So it's small in IA.
No, it is small n into capital L, which this is the total number of turns into IA. Because
Okay.
their I is the, I mean, current through each loop, where I is current through each loop. So for solenoid, this is the way of writing, right? And if you compare with the M equivalent into L, so the answer is how much? The M equivalent of solenoid is NI. Understood?
Yes, sir.
And this is actually J, if you realize. Okay, do you realize? No.
Yes.
So NI is the total current. Total length. So you can see it's following the same form, right? J, isn't it?
Yes, sir.
So in the examination, they may ask you, can you relate the pole strength of a solenoid in terms of these quantities? I hope you guys are getting this. Is it difficult?
No.
So you all understood this part?
Yes.
Okay.
Yes.
Now, once you think as a dipole, you know how to treat dipole from the theory of electrostatics. So you need to study again some typical thing. So imagine, okay, I will create a hypothetical magnetic field. So magnetic field induction. Due to hypothetical monopole. So we know monopole do not exist, but let's say if we do have a monopole, so monopole means like a point charge. So I'll do one by one. From electrostatics, we know at a distance r, what is the electric field? K cube r square, right? So similarly
Yes.
for monopole, the value of magnetic field will be K is mu naught by
4.
and m by r square. Okay. So if you think this is the formula, then the moment I give you a bar magnet, and you can take the geometrical length as the length. So this is like plus m is here, minus m is here. So can we find the magnetic field at the axial position? I hope you remember this. B at axial, also called end on position, similar to the electrostatics. So from electrostatics, what you can say? If the from center, if I take this as R, so how to find the B at this point? So the north pole will create B like this. So the north pole will create B like this, correct? Bn, and the south will create B like this. So BP is how much, guys? BS minus BN, right? BN minus BS, correct? And BN we can write as mu naught by 4 pi m by how much? So how much is this? 4 L by 4 AB. Okay. So the answer you can see. And again for dipole approximation, if you remember. Okay, we have done all this in this writing for the sake of completion. So it turns out to be mu naught by 4 pi, and it is same answer, 2 pm by RQ at equatorial position. If it is south, if it is north pole, equatorial means perpendicular bisector, right? So you can put a plus some positive percent. You can imagine the same way. So north will repel. You can put a north pole, hypothetical north pole. So the north pole will repel like this, isn't it? And south will attract. So the field the north will create is, let's say, B because south is also equidistant. Can we say this is also B? And therefore the resultant will be
Towards the left.
this is how much theta. So BP is how much? 2B cos theta. And what is interesting here to note that the dipole moment is from where to where? So dipole moment is from negative to positive charge, which is minus, south to north. So this is the dipole moment vector Pn. And the BP vector is exactly opposite. And if you substitute the value, let's substitute the B value, mean naught. And My R. So R square plus L square by 4 whole square is this much. And cos theta is how much? So for dipole approximation, so in the first case, the axial portion, the BP and PM are parallel to each other. So wherever is the BP, the same is PM. But for the equatorial portion, it is always opposite. So in vector form, we have to put minus sign. In value wise, we should remember, okay, this is like this. Any doubt in this so far? Tell me. Hello, tell me, guys.
No, sir.
No, sir.
It's a typical thing. Okay. So similar to the electrostatics, we do have the potential formula. What is potential formula due to a point charge? Tell me, guys. I hope you're getting this point. I'm not explaining anything because it is already explained in detail in electrostatics. I hope you remember this. Okay, I can
Yes,
only hope.
sir.
Yeah.
Sir, there's been music coming on and off for the last few minutes, sir.
Just yeah, it's outside.
Okay, sir.
Is it better now? Is it better?
Yes, sir.
Yes,
So for equatorial position, we know VP is Okay, you don't remember. Very good.
Yes, sir.
The north and south, it's a scalar, right? So
Yeah, it will cancel.
Yes,
cancel out. Okay. So I hope you remember this. Because both are at same distance. No? So plus m minus m will contribute equally positive and negative, and therefore it will cancel out. We do have a again for dipole approximation only. What we should remember for dipole approximation only. If I have a dipole, a bar magnet, a tiny bar magnet, and if I'm trying to find the B at some point here, R is much bigger than L, that is already considered. So it will have two components, as you remember. So the dipole moment vector is like this. So we can resolve this into two parts, one along this line, another like this. If this is PM, the blue one is, let's say, PM. If this is theta, so this will be PM cos theta. This is PM sin theta. So PM cos theta will create the dipole, the magnetic field vector this way. We can call this as a radial vector BR. And PM sin theta will create in this direction, opposite to the vector, right? Because for PM sin theta, this is equatorial position. I hope you don't realize. You realize.
Yes.
So do you all remember the electrostatics? Yes or no?
Yeah, ER and ET.
Yes, sir.
yes, sir.
So the BR becomes mu naught by 4 pi 2 PM cos theta by R Q. B theta is mu naught by 4 pi PM sin theta by R cube. Therefore, BP equals to under root of BR square plus B theta square, which is BP equals to mu naught by 4 pi into PM upon R cube into under root of 1 plus 3 cos square theta. Okay, I hope this is done. And in fact, everything else is also done. And you can call this angle as, this is BP actually, the net value. And this is alpha. So they may ask you what is tan alpha. Tan alpha is B theta by BR, which means this is tan theta by 2. This is very famous answer. Okay. So you should remember this answer. And what is the angle between the dipole moment vector and the resultant B vector? What is the angle between these two? Any guess? Let's call phi equals to. Okay, phi
Alpha
is
plus theta. Alpha.
theta plus, yeah, correct. If then this is again in general true. If phi is 90 degree, then theta plus alpha is 90. This implies theta is 90 minus alpha. This implies, okay, you can say better. I can say alpha is 90 minus theta. So tan alpha is cot theta, and then we know tan alpha is tan theta by 2 is cot theta. Therefore, this implies tan square theta is 2. This implies tan theta is plus minus root 2. This implies theta is value wise, we can say tan inverse root 2. These all are numericals which you can come across. We have discussed in electrostatics, which you don't remember. That's totally okay. Revise and get it. Yeah, I'm doing really fast. I know it. Okay, any doubt in this? You may have doubt, you can visit the electrostatics notes. So what we are studying is basically the dipoles, and therefore the answers will be similar to the dipole answer there. And similarly, the potential at general position. So the north, south, north, and in general position theta with this line R. So we know that it will have two components, PM cos theta. This is PM, and the other will be PM sin theta, which will not contribute anything. We know that PM sin theta will not contribute. So VP will be only due to the radial component, which is mu naught by 4 pi PM cos theta by R square is the answer. Then we have the relation, the BR we can write as minus 1 by R, sorry, minus del VP by del R. If you remember okay, I don't know. And this is by del theta or d theta. This is the answer. And if you take this formula and if you differentiate, we will get the BR and B theta again back. Anyone remember this from electrostatics?
Yeah, sir.
So the this is the polar coordinate system, and we have done something similar before. Okay.
Yeah.
So this is all from the your classical magnetism, and then we have the torque. We have the potential energy. So we can say torque on a bar magnet kept in external and uniform magnetic field. Imagine if you have a bar magnet. Everything is electrostatics. Just I'm writing so that you get some acquaintance with the way of writing. Okay. So I'm giving you the field towards the right. This is the B. We are supposed to think one by one, think of only plus M charge. For plus M charge, if the B is there, the force will be again compared from the electrostatics F equals to QE. So here the F equals to MB, right? And
Yes.
the directional force will be similar to what we have studied before. So north will experience force MB here, but south will experience force MB left. Field is uniform. These are couple force. If I say this is theta, this separation is L. What is the torque? So for couple force, the torque is force into separation between them, which is L sin theta. So it is ML into B into center. So the magnetic torque is how much? It is same to what we have studied already, PMB sin theta. We all know this. Okay. So we have done this in magnetism. For the loop, you can do it for bar magnet as well. So torque equals to PM cross B. Okay. In textbook, they use the symbol capital M for the dipole moment, but that's okay. So these are notational differences. That is okay. Oscillation of bar magnet. In uniform field. So bar magnet is like a rod. Depends on whether it's a cylinder or not. If it is cylindrical rod, if you think bar magnet is a cylinder with well-defined radius, the moment of inertia is going to be interesting. And this moment of inertia, you must remember. Why? Because it is given in textbook. It may come in the board examination as well. If your board is HSC, then you must know this answer. So this is R, and this is the axis passing through the center. Then moment to say about center mass is how much? It is ml square by 12 plus mi square by 4. So just remember this answer. R is the radius. And you can think as a diameter. If you think a small disk near the center, of course, I have done this derivation. You can check. Okay. So this is the moment of inertia about center mass. Oscillation will have the same formula. So we know torque equals to mb sin theta. So for a small oscillation, for a small deflection, and therefore we can say alpha equals to minus torque restoring upon moment of inertia about center mass. Therefore it is mv by I into theta. Then you can say compare with the omega theta. So omega square is under root of mv by I. Oh, this is gone. So time period is 2 pi by omega. So this is the answer. So we have done this before. You can do it again. 2 pi under root. If you want to write in PM term, you can PMB. That's okay. So we have done all electrostatics at once. Okay, I am not teaching. I'm just telling you. So potential energy of bar magnet, you can say. Accepting external magnetic field okay. So if we have a bar mat, because the torque restring torque is how much? Torque restring is mb sin theta. So the rotational work will be tau d theta, tau ext d theta, mb sin theta d theta from theta 1 to theta 2. So this will become change in potential is equals to mb minus cos theta 2, mb minus cos theta 1. So it is minus mb cos theta 2 minus mb. So we can say u theta 2 minus u theta 1 is this. We can say u theta equals to minus mb cos theta. We know this potential is minus pm dot b is the same formula. If you remember one place, you know at every other place. So anything else remaining, guys? Tell me. Is this clear?
Yes, sir.
Yes.
Yes, sir.
All right. So we are done with the classical magnetism. Nothing is left.
Dipole.
Dipole, yeah, the same formula. You can dipole interaction. So it's the same method. I mean, it is same formula. I mean, just symbolically it is same, no?
Yes.
It doesn't matter whether I'm writing for the dipole bar or it's a loop.
Yeah.
So the method is same. How to find? Write the potential of anyone. So
Potential.
U1 equals to minus P1 B2 or minus P2
B1.
B1, and if it is angle, then you can add cos it as well. And the force equals to, that's it. So you will get the answer. F equals to how much? 6 P1 P2 by.
R4.
That's it. Okay. So this is the same method. I mean, if you know magnetism, if you have studied there, the force interaction. I mean, symbolically the same. The dipole moment you have to replace by M into L for bar magnet, and there you used to replace by I into A, right? NIA. So the difference is in way of writing, but there is no difference in terms of concept. Okay. So anything else you want? Done. So we can move to the next concept called the earth magnetism, also called terrestrial. So earth magnetism, or you can say terrestrial magnetism. So first of all, let's try to understand what is earth. Okay. This is earth. Okay. So earth is orbiting in its axis, right? And if you think about the orbit around the sun, the axis of rotation is tilted by 23 degrees from the plane of rotation, isn't it?
Yes.
Okay, don't remember this. In case of rotation, if this is sun here, sun is here.
So 23 perpendicular to the plane of rotation.
That means every plane will have the direction by perpendicular, right? So this is the normal to the plane, right? And if I draw the earth here, so we know it is rotating by at something like this, right?
Yes.
And this is given 23 degrees. I hope this is correct. Okay. Now, what is the cause? I mean, see, of course, it was mystery for a long time, but what is the cause of earth magnetism? What creates the earth magnetism?
The Earth's core.
Yes, so core is in a plasma state. You know, the core of earth is so what is plasma? The fourth state of matter.
Yes.
So in plasma, atoms do not exist because what exists is only nucleus and the charge. Okay, and they kind of revolve. So as Earth is rotating, I mean, the plasma was also, I mean, it was rotating because it came from the sun. And this spinning plasma kept on spinning while the outer crust of Earth, gets cooled down over the period of time in few 100 billion years. And there was a incessant rain for the next few 100 billion years. And with that rain, the Earth crust got really cool. And we got the atmosphere, which is like the insulating layer, which prevent the heat radiation back to the universe or the space, outer space. This is the greenhouse effect. But also that kept the plasma in the same state. So plasma is still the representative of, you can say, the sun. So Earth is also a sun in its core. It is similar to sun in behavior. And that plasma is a large carrier of charge. And because of the rotation of that charge, it is able to create its own magnetic field. Now that we call the Earth magnetic field. And as the Earth axis got tilted, the plasma was not able to tilt by the same value. So what we assume that the plasma, I mean, the rotation of plasma effectively is close to 11 degree. Okay. So if I take the Earth vertical, then our magnet is something like this. And it is certainly not 23 degrees because Earth has tilted maybe by that value, but the plasma has not tilted by the same value. So it is found that, okay, this is roughly 11.2 degrees, Sambhukarati 11.5. Okay, I'll take 11.x degree. I mean, roughly that value. Okay. So this is somewhat tilted. This is called the magnetic axis. So let's call this is 11.2 degree. So this axis, the vertical which I have drawn, this is actually representing the physical North Pole and physical South Pole of Earth. And this axis is called the geometric axis. But the core is representing some somewhat tilted direction. And if we draw an equivalent magnet here to represent the Earth core for its behavior, then this is called magnetic axis. So the geometric axis and magnetic axis are two separate axes, and the pole on the axis of magnet, this part, what we call? So this is called the magnetic North Pole, and this is called the magnetic South Pole. Okay, so there is a device called compass, which is made of the a magnetic needle, and if you try to follow the compass on Earth, you will not reach the actual North Pole of Earth. What you will reach is the magnetic North and magnetic South Pole. What is the definition of magnetic North Pole? You know what is the definition? It is the pole, it is a place near the Earth at which if you suspend a magnet, which is well defined, then the North Pole will face towards the Earth's surface. That's called magnetic North Pole. The definition is very interesting. What is the definition? If you hang a magnet, then the North Pole of magnet will, face the Earth. And when this is possible, it is only possible when here it is. You can see now. What is here?
South Pole.
Because South can attract the North, isn't it? So the magnetic North Pole is basically the South Pole of Earth magnet. So by definition, we say North Pole is the point at which the North Pole of magnet will face the Earth, which means the South Pole is here. And similarly, what is the magnetic South Pole? It is the place at which the South Pole of magnet will face the Earth. So when the South Pole will face here? When this is North. Is this clear? Tell me, guys.
Yes, sir.
Yes, sir.
And now, if you think as a bar magnet, you can exactly draw the lines of force. Okay. So let me do something not difficult to do. The latitude, longitude, but anyway. Now we divide the Earth into two separate parts. So one part we called, what to call? This part is called northern hemisphere. This is called southern hemisphere. So we divide the Earth into two parts, northern and southern hemisphere. Okay. Now, what is the speciality of northern hemisphere? If you are in the northern hemisphere, how will you come to know technically that you are in that part of Earth? Any guess? I give you a magnetic compass or a magnetic needle. And you have to just tell me that whether you are in which part of the earth, northern or southern. What will do?
Sir, the North Pole tilts downwards if we like suspend it.
Exactly. So if you are in the northern hemisphere, the North Pole will always tilt towards the surface. Even it is facing or not, but it will tilt towards. It means the northern will be closer to Earth and southern will be away from Earth in a freely suspended magnet. Is this clear? Yes or no? Hello, guys, tell me.
Yes, sir.
Yes, sir.
Yes, sir.
So in the northern hemisphere, if you are there, it means any freely suspended magnet will have North Pole closer towards Earth or tilting towards the Earth. And if you're in the southern, the South Pole will be tilting towards the Earth. Is this clear? Hello, hello.
Yes.
Yes, sir.
Okay. Now you can draw the field lines to understand what exactly happens. Let me do it separately. So compass is like the the oldest GPS navigation system, right? And you know why the Captain Jack Sparrow was so famous. So it is all about the compass, right? Because when you're in the middle of ocean, can you see the north, south, east, west?
No.
So the only way you can sail through is the compass. I'll teach you how to sail using compass. That's our next goal. So this is the which pole? Tell me. The upper end is which pole? This is south pole of magnet, correct? This is north. Always remember that the south and north of the earth magnet is opposite of the earth, north and south of earth. That's logical, okay? Because the definition given is that way only. Okay. So how to do the lines of force? So lines of force will start from north. And after coming out of north, it will something like this. Into a better one. Okay, really poor diagram, but okay, I tried my best, but sorry. So you can see the diagram in SC whatever. Okay, what is the idea is, if you draw the diagram, you can see one thing. The magnetic field lines will be close to, or you can say parallel to the Earth's surface near the equator, isn't it? So if you draw any equator, let me do this random equator. So almost close to equator, can we say the field lines is parallel to the Earth's surface? Isn't it? Because of symmetricity, we can say it will
Yeah.
be parallel. So
Yes.
Earth's magnetic field is parallel to the Earth's surface near the equator. As you move up towards the north, the field lines is like this. You can see this is the B direction. So B is the north is this way. So if you want to resolve, you will get two components, one towards the Earth, another parallel to the Earth, isn't it? So every magnetic field will have two components, one towards the Earth's surface, which is like called the vertical component, another horizontal, which is parallel to the Earth's surface near that location. And if you reach the exact pole, the vertical component will survive and the horizontal will be 0. And near the equator, what we can say, the vertical is 0 and horizontal is, so the net is only horizontal. But at any other place, what we can say? At any other place, we can say the B will have two components, vertical as well as horizontal, isn't it? Hello. Tell me, guys, yes or no?
Yes.
Okay. So we have to define two concepts, which is most important. That's called the geometric meridian. We call GM. And what exactly is this geometric meridian? So when you are standing on the Earth, of course, you don't see Earth as a round object. You see the Earth as flat object. So if you are standing near the Earth, can I draw the Earth as flat surface like this? I'm taking the the x-axis here, the y-axis here. This is the horizontal, and the z-axis representing the vertical. So geometric meridian, how to draw the geometric meridian? At any point in the Earth's surface, wherever you are standing, draw a plane. Or simply draw a perpendicular. I don't know where it is, but you have to draw a perpendicular. Okay. And the perpendicular must contain the geometric axis. It means if I extend this plane, it must contain the Earth geometric axis. And if it is containing the Earth geometric axis, it is called the geometric meridian. So you can say definition is, it is a perpendicular plane drawn on the Earth's surface which contains geometrical axis of Earth. Don't try to realize this, it is something like this. Okay. So even if you don't really understand what exactly is happening, it's okay. So GM only means draw a line and draw a plane on the Earth's surface, and imagine it is containing, the extension of this plane is containing the Earth's geometric axis. That is the only idea. Okay. Now at the same point where you are standing, if you draw a plane which contains the magnetic axis of Earth, we call it magnetic meridian or MM. So the second definition is so again you can do the similar definition. It is the vertical plane which contains Earth's magnetic axis. That's it. Now, one thing is sure that because of the inclination of geometric and magnetic axis of Earth, these two planes will never be same. So if these two planes are not same, then if I call one of the planes as GM, then how the MM will look like? So it will look like this. Slightly tilted. So if one represents GM, then other represents MM. And you will always see some angle between the two. And this angle we are going to call very soon. This theta is called angle of declination. So what is the angle of declination by definition? Tell me, guys.
The angle between
The angle between.
Yeah. It is the angle between the geometric and magnetic meridian drawn at a point on the Earth's surface. So that is a simple definition. Let me just put the definition quickly. It is the angle between geometric meridian and magnetic meridian drawn at the same point of Earth. Of course, you can't draw the geometric meridian in London and magnetic meridian in Hong Kong, and you can find the declination. So it must be at the same place. So we call the angle of declination. Now, what you need to understand certain things. The Earth magnetic field will be part of which plane? Geometric plane or magnetic plane? Tell me.
Magnetic planes.
Magnetic.
So always remember that the Earth's magnetic field is always part of the magnetic meridian. Okay. So whenever you want to draw the BH or BV, hypothetically assume this as MM. And if you are in the northern hemisphere, how the bar magnet will incline? The tip of the bar magnet will be down or up?
Down.
Down. So if I'm drawing something like this, I can do it separately here. Space constraint. I'll do it here. That's better. So if you are in the northern hemisphere, and see the southern, so in the northern hemisphere, the North Pole is always down. So the Earth resultant field, the net field is always something like this. And this angle that the net field makes with horizontal, this is called angle of dip or inclination. So I will not use inclination, I will use declination, dip only, because inclination and declination may confuse you. So remember that declination is only for the meridian angle, and dip is the where the compass can point out if suspended freely in the Earth's magnetic field. So that for dip angle we use the symbol delta always. And this B will have two components. One will be BV, another is BH, and you can clearly see that tan of delta is how much? So tan delta, what we can write in terms of component? It is always BV upon BH, right? Or you can say BV is B sine delta and BH is. But if you are in the southern hemisphere, the same magnetic field will point away. But by definition, we always call this as a dip angle, and we take from horizontal. So the BV in this case will be upward and BH horizontal. Is this clear, guys? How to draw the... Now, how the dip angle is interesting. Tell me, guys, as you go from equator towards the pole, the dip angle will increase or decrease?
Sir, I have a doubt.
Yes, please.
Sir, I don't understand, like, is the diagram 3D or 2D, sir?
Which diagram? The second one, the first one?
Sir, both, sir.
Every plane is 2D and it is vertical plane. These are representing the vertical plane, which, let's say, if this is the Earth's surface.
Yes,
If you're
sir.
standing here, so your plane is something like this, right? So you're drawing two verticals. That's it.
Okay,
So
sir.
Earth is so big that if you draw a tiny vertical plane, it is almost vertical to the surface, right?
Yes, sir.
So both are standing on the same surface, right? And because both are supposed to contain the different axes, one is trying to contain the geometric axis, other is trying to contain the magnetic axis. So they will have some angle which we call angle of declination.
Declination.
Okay.
Yes, sir.
And once we have a magnet in the magnetic, see, every magnet is by default in magnetic meridian. Understood?
Yes, sir.
So if there is a freely suspended magnet, the torque will be zero in which direction? When the magnet dipole moment will align in the direction of net field. Yes or no? Tell me, guys.
Yes, sir.
Is this clear?
Yes, sir.
So in the magnetic meridian, there are two things which you need to understand: how to draw B, how to draw BH, BV, and dip. Now tell me one thing: as you move from the equator towards northern hemisphere, I mean North Pole, the dip will increase or decrease?
It will increase, sir.
So at the pole it must be 90 degree,
Yes, sir.
and at the equator it must be 0.
Yes, sir.
Yeah.
So first of all, let me put the definition, then we'll go and explain that down. So the angle of a dip or inclination, how we define? Tell me, guys, what to define, how to define? It is the
Angle made
angle
between the
made
suspended.
by a resultant magnetic field of Earth in which meridian?
Magnetic meridian, sir.
Magnetic meridian. So when you find the answer in the magnetic meridian, it is actually called true dip. So by default, dip means true dip. But we will also come across something called the apparent dip, which we obtain in the geometric meridian. And how we do so, I'll explain later in a short while. So true dip is, so simple fact is, true dip is always measured in the which meridian?
Magnetic.
If dip is measured in, so if dip is measured in G, if dip is measured in GM, it is called, what do we call? Apparent dip. So one should be aware of these definitions: that true dip, the angle of declination, magnetic meridian, and geometric meridian. Every question we can solve if we know these facts. That's it. So let me do once again. So to solve any question of earth magnetism, what one should be aware of? This diagram is called the base of all questions. So without any, it's like no brain. So whenever you are attempting question of earth magnetism, without much thinking, draw this diagram immediately. Name one meridian as magnetic, other as geometric. So let's say this is magnetic. Let's say this is geometric. Step 2. Always draw the BV and B, H. So in the magnetic meridian, we know it is BH and this is BV. So what is the component of BH in the geometric meridian? What is the component? Tell me, guys. If this is theta, this component of B will be how much?
BH cos theta.
And what is the component of BV in the geometric meridian?
Sir, the same.
Same. Yes. So if you have a geometric meridian, and if you know the component is BH cos theta, and it is BV, if I force a compass to remain in this plane, and if I make, okay, let's try to, okay, I'll give you the example how it is confined in that way. So let's say we have a glass case with a needle which is intact. So this is north pole of the magnetic needle. This is south pole. This is it is hinged here. And if you remember that in a compass, the needle can only turn parallel to the plane, isn't it? Can it bend left or up and down?
No.
So it is just like the needle of your watch. It is kind of hinged, and even it wants the BV cannot do anything to this needle, isn't it? Okay. So if you keep this magnetic compass on a Earth surface, what will happen? The north and south will align in which direction? Which meridian?
Sir, the magnetic meridian.
Yeah, so that is how we actually find the magnetic meridian. Say, if you put this compass on the Earth's surface, you can always see there is a particular alignment. And then you draw a plane like this. And once you draw like this is your, what is this? This is your magnetic meridian. Do you realize this? Because this, this compass is free to move in the horizontal plane. So when a magnet is free to move in the horizontal plane, it will always align itself in which direction? B, BV, BH. How this needle will align itself? Tell me.
BH. Sir.
Along
Exactly. Along
BH.
BH. Do you all realize this part? So BV cannot do anything, right? Because of the construction. So the constraint we have put because of the construction will not allow BV to do anything. So now BH is the only thing which can do. And once it will align, you can exactly know what is B. What is B? What is MM? What is the magnetic meridian? Understood? So this is how we find the MM. That's technically we do it. Now imagine if I make the compass vertical. So a vertical compass, I can draw the same compass like this. Let me extend this line. Sorry. Imagine if I draw a compass like this. So once you make this compass vertical, keeping the plane in the magnetic meridian, what will happen to this North Pole? Will the North Pole go down or up? Let's say it is northern hemisphere. If it is northern hemisphere, what will happen to the North Pole?
It will go down, sir.
Now the BV will come into action, right?
Yes, sir.
So the moment you know this is the magnetic meridian, and the moment you tilt this compass, now the vertical motion is possible. Now it can turn like this, right? And once this will happen, your north pole will dive down. Just a minute, let me pause. So what is this angle? This angle is, this is the true dip. Do you realize this? Hello guys, tell me.
Yes, sir.
So once you make it vertical, it will actually show you the true dip. So this is the rule. To find the magnetic meridian, you take a compass, put it horizontally, just put on the earth surface, flat surface. You see the alignment of north and south. Create a plane like this, you know this is the magnetic meridian. And once you get this meridian, make the compass vertical. I mean the plane of compass as vertical. The needle will dip immediately. And it will show you the true dip. Do you realize this? How the true dip we are measuring? Hello, hello. I
Yes,
think
sir.
not all are getting. Yeah, tell me, Darsh, Krishiv, Garv, Parth, Manav.
Yes, sir.
So, do you realize that how to get the MM and how to get the dip and how to get the plane of the, magnetic field?
Yes, sir.
You can think this way.
Yes.
A magnetic meridian is a plane in which the magnetic field lines are parallel. Think that way. That's easy.
Yes, sir.
So the magnetic field lines will be always parallel to this plane. That's why it's called the magnetic meridian. Geometric meridian is somewhat tilted. So imagine if I tilt this plane, I want to show the plane of the compass like this. Look at this carefully. This very carefully. If I make this plane something like this, what will happen? The dip will remain same, or dip will decrease, or dip will increase. What do you expect? Keeping the plane of the compass vertical, if I tilt something towards me, if I tilt this plane something like this, what do you expect? The dip will change, decrease, increase, remain same. Any guess?
It should increase
So it will increase.
Definitely. Why should it increase? Any guess?
because the
So
horizontal
because the
component is
BH
decreasing.
component becomes lesser.
Exactly. Because we know that this is BH. This is BV. But as you tilt, the BH itself will decrease by value BH cos theta. Let's say theta is the tilt. But BV will be unaffected. So because the vertical component is unchanged and the horizontal has decreased, so dip angle will increase, and that same will happen here. So if I draw something like this, and now I know this is the del dash. So what is 10 del dash? What is del dash here? This is called the apparent dip. So here del dash is and you may be asking, sir, why we are finding this apparent dip? This dip is not in the magnetic meridian. It is in a plane other than magnetic meridian, isn't it?
Yes.
Okay. And now you may be wondering why this is required. Imagine you are the Captain Jack Sparrow going into this Atlantic Ocean towards the pole. If you exactly follow the compass, the north pole of compass, if you're keeping the compass horizontal trying to follow the north pole, where you will land? On the geometric north or magnetic north?
Magnetic north, sir.
Magnetic.
And see, the degree is small, but the Earth radius is so large that you will be far from the North Pole, isn't it? So we know the separation is on the Earth's surface. If it is 11 degree, this is how much? R theta, right? So S equals to R theta, isn't it? So even a small angle will throw you far away on the Earth's surface, because this is, and theta is how much? Let's make it simple, 10. And this is 3. Very expressive. Almost R by 6, which is how much? It's roughly 1100 kilometers, right? Imagine a person following the compass exactly will land from its destination by 1100 kilometers away. So that is what you don't want to do. So what you do is you try to change the angle. The declination is known for every location in terms of it is kind of mapped already by the earlier voyagers. And by tilting the compass, by keeping vertically, we check whether the dip is decreasing or increasing. If you tilt away from the magnetic meridian, what will happen? Dip will increase or decrease? Away from magnetic meridian, the dip will always increase.
Increase.
And towards the magnetic meridian, it will
Decrease.
decrease. So that is how we understand whether we are going towards the actual pole or away from the pole. And by suitable adjustment, we can actually sail in the correct direction. Of course, you need some more idea for more knowledge. But as of now, you can understand that this is how we do the navigation. Now, so what is the apparent dip here? 10 of delta dash is how much? Tell me, guys.
BV by BH cos theta.
Yeah, it is BV by BH cos theta. And therefore, can we write this as tan of true depth upon cos theta? So this is all formula you're not supposed to mug up. If you know how to do these simple diagrams, this page is good enough to solve every question of JEE-Mains from this topic of. It is clear?
Yes.
So how we determine the dip at any place? It's simple. You take the compass, find the magnetic meridian first, tilt the compass, make it vertical in plane. You will see the true dip. Okay. I hope this is clear, right?
Yes.
Yes.
Also, you can add one thing. So it's a very famous question from this chapter, which was asking the NCERT having this question. It's a very kind of heritage problem. So what is given to you? You know the dip. You know the dip angle in the magnetic meridian. So it means you know the true dip, right? And we know that true dip is how much? Now what we do is we draw. Okay, see, we don't know what is meridian and all when which geometric meridian we are trying to find. But what we do is compared to the magnetic meridian, I will take two complementary plane. You know what is complementary plane? The plane whose sum of angle is 90 from magnetic meridian. So let's say this is GM1, and I am taking the GM1 like this. I'm taking this angle as theta. This is the GM1. I'm taking the another plane. GM2. and this makes an angle 90 minus theta. So can we say the GM1 and GM2 are complementary planes correspond to the magnetic meridian? So what you can say here? Let's let me write down. So let let GM1 and GM2 are complementary planes with respect to magnetic meridian. Okay, so now I can draw it. Separately. So one thing is clear that this will be BH cos theta. This is BV. But what is this value? Any guess? This is BH.
BH sin theta, sir.
Very good. So the dip that we will calculate here will change in both cases, right? So this is called the delta 1, or you can say delta dash. This is called delta double dash. So these are two apparent dips. Now question is, given the two apparent dips of the complementary plane, can we find the true dip? Or simply, what is the relationship between delta dash and delta double dash? Find the relation between delta and delta double dash. Find the relation between all three. So what we can write? Okay, tan delta dash is how much, guys? Tell me.
Tan delta by cos theta, sir.
Yeah, so I can write directly. It's okay. And tan delta dash will be how much?
Tan delta by sin theta.
And because theta is the variable, can we eliminate theta from this two equation? So we know the answer. Sin square theta plus. And that is the best way to eliminate. So we can write tan delta upon tan delta double dash whole square plus tan delta by is this clear, guys? So this implies cot square delta or cot square true dip is cot square delta plus cot square delta dash. So this is a very famous relation, and you may come across this question itself. The relationship between the true dip and apparent dip. So given the apparent dip in the two complementary planes, we can find the true dip in the magnetic meridian. So this will be your, you can say, the challenging problem. It's clear? Hello, hello.
Yes, sir.
Okay. So this is all from the Earth's magnetism, but we have something more. So now what you are supposed to remember is a noise. Tangent galvanometer. What is galvanometer? So it's a current measuring device, right? So before I design this instrument for you, just remember some basic fact about this galvanometer, how we design. So what we do is we always take a magnetic compass in which we will have magnetic needle, which is kind of hinged to a plate, and so it can move parallel to the surface of the compass plane. It will have the transparent glass case so that you can see through it. Okay. So the compass is something well defined, or it is manufactured with some standard. The magnetic needle is a lightweight magnet which is very sensitive to the slightest external magnetic field. So even a slightest field can rotate it very easily. Okay. So what we do is generally we take a big, kind of loop. So imagine there is a big loop here. It's really big. And let's say there is a large number of tons of wire which is wrapped here, carrying current I. And this is having very large radius, small r, but let's call this as small r. So what is the magnetic field at the center? We know the answer. B at center is this is the number of turns is n turns. So B at center is how much, guys? Tell me.
Mu naught ni.
Mu naught ni by
By
it's a ring, no? What's the formula?
by
2 or so.
Very good. So it is mu naught I by 2r into n. Now this magnetic field is acting as the external field, and this external field is proportional to current. Okay. So this is the EXT which we generally create. You can choose any mechanism, but generally it should be current-based mechanism for the creation. And we take R to be really large in size so that the compass we can treat exactly kept at the center. So here is the compass. And the compass is kept horizontally. Okay. So how this loop will create the field at this point into the plane? Isn't it? So this BXT is into the plane. Understood? Hello, hello, hello. Hello,
Yes,
guys.
Yes.
All right. So this is the plane. It is perpendicular. And the earth magnetic field at that location will be it will have two components, isn't it? So which two components? It will have BV and BH at that location. Okay, and our compass is horizontal. So which component can affect my component? I mean my compass.
BH
So-
components.
Yeah, so BV will do nothing, right?
Yes, sir.
Okay. So generally we take a large loop to create this galvanometer, and we put the compass exactly at the center in horizontal position, and the compass experiences two two field lines, one due to the current carrying loop, another due to the earth magnetic field which is already present. So this diagram will not make sense to you, so I'll draw the next diagram which will make sense to you. And there are certain rules. So imagine this is the so this horizontal line is representing this is horizontal line, and this is representing the external field which you can produce by any mechanism, but let's call this is BXT, and it should be current based mechanism. Okay, produced by current carrying loop. And the earth magnetic field is also horizontal, but when we design this device, we try to keep these two planes mutually perpendicular. I mean these two directions mutually perpendicular. So I'm going to show you the earth field exactly in this direction. It is vertical. And what you're looking right now is the horizontal plane. It is not the vertical plane, it is purely horizontal plane. Okay. Anyway, so now we have the BH. So we have BH, we have B external, and this B external is created by any mechanism. It should be only current based mechanism. So you can say this B should be proportional to I by any method. Okay. So that's the whole idea. I have given you one example. It's a mu naught NR by 2R. You can choose something else. You can take the compass exactly at the center of a very large giant solenoid. That is also okay. But in any case, it should be proportional to the current. Okay. So I hope this is clear. So far, so good. Okay. So what do you do next? The next step is draw the compass. So let me draw a compass somewhere here. So compass will have two parts. So generally compass comes with a two color shade. And one color is taken as north, the other color is taken as south. It's a very tiny needle. I am just drawing it bigger. Like this. And now why I have drawn like this? Any guess? Because of the North Pole and the South Pole are under the action of two fields, right? One field is horizontal. So North Pole will experience force like this. How much? M times BH, just like Q into E formula, if you remember again.
Yeah.
Sorry. M times BX2. And the same North Pole also experience force like this. How much? M times. Tell me guys, how much? BH, right? Is this clear how the force is applied?
Yes, sir.
Yes.
But what about the South Pole? The force will reverse. MBH and MBEXT. And then the dipole axis, which means the axis of this needle, will make some angle with the earth magnetic field. We always take the angle from the earth magnetic field. This angle we call, let's call theta. If this is theta, this will be also theta. And at equilibrium, the net torque is 0, which means the theta will be how much? Can you guess the theta? It will always align in the direction of a resultant field, right? So what is the resultant of BH and BV? I mean BH and BEXT. It is along the line, no? So at
So
equilibrium,
tan theta is
Yeah.
equal to B extreme by BH.
exactly. So tan theta is BEXT by BH. Is this clear to all of you? And therefore, the BEXT is how much? And BEXT represents any current based formula. So BEXT can write as something C into I. I mean, of course, I can write here the full formula, but any constant to I is also sufficient. So we have mu naught NI by 2R. And this is BH. So I is how much? 2R BH upon mu naught N into. And because of this particular relation, the current is proportional to tan theta. We call it tangent galvanometer. So the name is clear why it is called tangent galvanometer. This is called tangent
Yes.
law. So this is called tangent law. So how to derive the tangent law? It is very simple. Draw two B values, both are horizontal. One must be BH, other must be due to some current source. The compass will align in the resultant field direction. We always take theta with respect to BH. If you have confusion, if someone is showing BH horizontal, I will shift the theta there. So what you must remember, that theta is always measured with respect to what? BH. So imagine if I switch off my loop, if the current is switched off, what will happen to the compass? The B external will vanish and my compass will turn back to BH, isn't it? Hello, hello.
Yes, sir.
So as I grow the current, the compass will start tilting away from BH. And as current will grow more and more and more, the theta will grow accordingly, isn't it? Hello, 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 guys.
Yes, sir.
So the current and the tan theta are proportional. Or simply you can say, by suitable calibration, by looking at theta, can we find the current also?
Yes, sir.
So when you use compass for the measurement of current, then such device is called tangent galvanometer. I hope this is clear to all of you. Hello, guys, tell me.
Yeah.
Yes.
So now we describe something called sensitivity of tangent galvanometer. Sensitivity of tangent galvanometer. So how we find the sensitivity, guys? Tell me.
Sir, I by theta.
Yes. So here, I we got is k sin k tan theta. So di will be how much? So di will be k sec square theta d theta. And to get rid of k, we can write that di by I equals to how much? Now this will get rid of sorry, this theta. So sec square theta by sin theta is how much? Sec is cos, right? So it is I upon so it is I upon sin 2 theta by 2, right? So di by
Yes.
d theta is how much?
Sir, current sensitivity is d theta by di, sir.
Yeah,
When
I'm
you
going to
split
reverse
over
it.
the-
Yeah, I'm going to reverse it. So d theta by di is how much? So the current sensitivity is deflection per unit current, right?
Yes, sir.
So the answer what you'll get here is sin 2 theta by 2i So tell me when the sensitivity will be maximum. So for maximum sensitivity, any guess?
Sine 2 theta is equal to 1, sir.
Theta equals to
Pi by 4.
pi by 4. So from this tangent galvanometer, the direct question that you can expect is at what angle the sensitivity is supposed to be maximum. This is the first question you will come across. Understood? Hello, hello.
Yes, sir.
So from this topic, I mean, what they generally ask is the angle at which sensitivity is maximum or something like that. Okay, we'll see the question which they have already asked. So now we are going to do some devices. This is the last page. Anyway, let's see how much we can complete. So the next device is called deflection magnetometer. So what is the purpose of deflection magnetometer? So when you have a tiny bar magnet, and if you would like to know the pole, the dipole moment of such bar magnet, then this method is very nice. So it is used to determine the dipole moment of bar magnet. Generally, we take tiny bar magnet, a small one. So dipole moment, you can find it easily. What we use here? So we use a bar magnet. So here, the B external is produced by bar magnet, and it is also based on tangent law of perpendicular fields. I should have mentioned this extra suffix. So here, when we are deriving this formula, we took intentionally the two fields mutually perpendicular. So that's why this is called tangent law. I have written somewhere tangent law. Yeah, tangent law of so all devices we are going to study from now onwards will be based on the tangent law. Let me put a heading like this. Tangent law. As you will say, sir, you haven't taught because it's written here. So we are going to design this. So here the rule is simple. The B external, earlier we had a current carrying device. Now the B external is produced by the bar magnet. And as I said, we have to keep these two mutually perpendicular. So there are two ways in which you can achieve this. So one is called the. Okay, first of all, let me show you the device itself. So we have a large scale. So there is a round case, and this case is actually supposed to keep the what? Keep the compass in horizontal position. So let me show you in short how it looks like. So we have a compass, and it is having inbuilt scale attached to the side arms. And the good thing is that you can turn the arms around this compass. Okay. So that is the arrangement. Okay. So we have two methods, I mean, two separate ways of doing this. So there's something called, okay, to go to the next page, because we don't have page, I'm going to stop sharing, log in again after 30 seconds. Okay.